using QP trick, instead of the probability half, we got something like this. Even in fact, if you take that angle equals to 1 degree, okay, this particular angle, if you take in fact 1 degree, then this probability of getting 0 and probability of getting 1 will be 0.9999 and 7.610 power minus 5. And then if you take this phi equals to 10 degree, right, then probability of 0 and probability of 1 from the quantum measurement will become 0.9924 and 0.007596. Now you learn, or you know, that how to play with the probability using the entangled operation, or in fact you can say simply quantum interference, right? You create the interference of the information such that the probability instead of half become this much and this much, right? You check the probability of 0 and 1 is highly different by just changing the phase, and that phase you have used as an entangled phase gate, right? So total probability, okay. So this is just approximations, right? Of course, the total probability should be theoretically 1, but I just wrote in this way. So there are other points, right? Decimal points. So I took some value from the computer and just displayed it here. So the actual value will be slightly more terms, right? So such that the total sum of this plus this equals to 1. That should be the quantum postulates. Okay. So we need to perform many experiments to get these amplitudes or the probabilities. Okay. Now I have now how to get the precision. The experiment that I have shown, the QP trick, has uses. I have done measurement only on the single qubit, right? I have measured only on the single qubit. So the precision is very less. To get more precisions, so more precisions if I want to get, so then I have to use more qubits. Because 0 creates how many possibilities, right? So 0 and 1, right? So if you have n number of qubits, so you can create 2 to the power n basis states, right? Basis states. So 2 to the power n basis states, you will be getting one of those basis states, right? So here you have more precisions to define your binary strings, right? So here only one. If you create a string like this, many 0, many 1 and all, so then basically, so it will be more and more precise to for the estimation. So now design a circuit something like that. Suppose I take n number of qubit, 0 tensor product n, okay? So suppose 1, 2, dot, 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 many, okay? And this particular state is 0 tensor product n, okay? And then I apply a series of Hadamard gates. So instead of writing individual Hadamard, I am putting Hadamard tensor product in, means in each chain or each line, you put one Hadamard. So this is a tensor product of Hadamard, right? Now you take a composite state psi, or you can take a single state psi as well. Normally you need a composite gate to define any signal, right? More number of terms, it's not just a single term. So this is often called a target state. And this n qubit is for the measurement. So these are the measurement qubits. Measurement qubits. And these are the target qubits. So suppose these are my target qubits, right? Now what I'll do, so I will create an operator, U operator, as in power of 2 to the power n minus 1. And I'll apply multiple such operations up to n times. Okay. U 2 to the power 2n minus 1, U power 2 to the power 2n minus 2, up to U2 to the power 0. So this much operation I'll perform, and I'll create an entanglement or the controlled operations from first qubit to this particular operation, this to this particular operations, up to this to this. So if I can do up to this, what will happen? So let us try to unable to see the screen. Uh, if, is my screen not visible, or is the problem? Can anyone just confirm, or otherwise I can reshare? It's visible, right? So those who cannot see, please rejoin. Maybe from internet issue from your side. Right. Thanks. So now again, just this is a augmentation of the circuit to the higher number of precision qubit as well as repetition of the control operation. What will happen? Okay. So let's do this way again. This particular way, if we see, we won't do the measurement, but we'll see something. Okay. So what is happening by doing these things? So step zero. Step zero is fine. Step zero is just we started with O tensor product N and the state kit psi. Okay. So now step one, we apply it the state. So Hadamard, mini Hadamard. So 1 by square root 2 or N and 0 plus 1, right? Tensor product N and the state psi. So that is basically my uh, step at this output here. So this is the step 0. This is step 1. This is step 2 up to step N. Okay. So this is my first step. And what is happening? Let's wait here. Okay, before going to more steps. So let's wait here. So in this step, so what we are doing, we are applying, suppose u2 to the power x. So x is some number. Say u2 to the power x. Let's take this one. So this is equivalent to basically, because we are multiplying, basically we are applying the gates multiple time with the power 2 to the power x, okay, n minus 1, n minus 2, and 2 to the power 0, right? So u2 to the power x psi, that is multiplying the matrix multiple time up to x number of times, right? So we can rewrite this equation as u2 to the power x minus 1, right? u2 to the power x minus 1 times u times x. This is same, right? And this is equivalent to what? This is equivalent to basically u is what? U. So we have learned that u ktex equals to e to the power I phi ktex eigenvalue equation, right? This is the eigenvalue equation. So we can write from the eigenvalue equation. So this part we can write u2 to the power 2x minus 1 times e to the power I, we can write it as phi angle as phi e to the power I phi, okay, ktex, right? There is no issue, right? So this is also equals to, we can also further break these equations to e to the power I phi into e to the power I phi, and so into u to the power 2x minus 2 into psi, right? Again, we can take another term from here and we can write this way, right? So if I repeat this step up to step N, so what will happen? It will create 1 upon square root 2 whole to the power N. So ket 0. So just remember the yesterday how we have broken the equation in the similar way, right? So ket 0 plus e to the power I phi and I phi into 2 to the power n minus 1 ket 1. So this is coming from this first gate. So the first gate phase is what? Phase is 2 to the power n minus 1, this power. So this is coming here 2 to the power n minus 1. And if you apply a controlled unitary operation on the first qubit, so that particular phase will be added to the in front of the ket 1, right? Ket 1, and ket 0 will be intact. There will be nothing. So as you can simply compare between the previous QP and the trick that we are doing here for multiple number of measurement qubits here, right? Okay. Okay, so just a confusion. So this angle will be phi. Okay, if I make some mistake, please rectify. Angle I have taken as phi, and quantum state I have taken as psi. Okay. So this should be the notation. If I have made some mistakes, so please rectify it. Okay. So sometimes I have written say kit psi, here it is as x, so it should be psi actually. Yes. So I was just bringing this concept here. Okay. So let me rectify this part. Thank you for just raising this point. Right. So how I initialized. Okay. And x is some arbitrary number. X can be x. X means you are anywhere in the circuit. N means you are in the initially. 0 means you are at the last. Okay. So so at nth step it will be 2 to the power n minus 1 gate 1 tensor product. So this is the first for the first gate. Now for the second control due operation, what will be your state? Your state will be gate 0 plus e to the power I phi 2 to the power n minus 2, right? Is the fetch factor, right? Gate 1, again tensor product, and it will repeat. And you will be end up with the last state will be gate 0, e to the power I phi, and 2 to the power 0 is the last phase factor, right? 2 to the power 0, that is 1, gate 1, right? So we can see the coefficients all are added in the numerator basically here. So let's compare this particular equation. So this equation, say this equation number equation 1, say, okay, equation 1, and let's take another the let's compare it with the QFT equation. What was our QFT? Quantum Fourier transform x tilde equals to 1 upon square root n. N is basically again 2 to the power n, right? So this factor is same. 1 by square root n and 1 by half whole to the power n, basically the same thing, right? Then gate 0, yesterday we have derived it. I'm just writing the last expression, the final expression. So 2 pi I x by 2 to the power 1, gate 1, tensor product with 0 plus e to the power 2 pi I x by 2 square, gate 1, right? So on. And the last particular value was 0 plus e to the power 2 pi I x by 2 to the power n, gate 1, right? And at the end it was gate psi, right? Now now if we compare the output of the QP circuit, actually this is not the entire QP circuit. So till now what we have designed like this way, we are here, right? So till here the output state here, this particular state is this expression, this equation 1, right? Step in. And the QFT looks like this. So if you compare these equations to this equation, this is same, right? Let's take blue color. The final state, that is some multiplication of gate size, say for example. So this is same. And if you all compare all these things, so what we are getting? So if you compare this QFT versus QP up to this particular generation of the circuit, we see that this particular factor is coming in the denominator, right? Denominator. And the phase factor that is coming in the QP is in the numerator, right? Right. And hence you see whatever angle that is the phase that is we have that we have in the QP circuit, that is the phase phi in the QP, and in QFT it is actually this phi by 2 to the power n into 2 pi. There is one another factor, 2 pi factor is there, right? So there is no 2 pi factor, but there is another 2 pi factor is there, right? So hence, so this is the circuit that we have designed, and the QFT circuit, they are very much similar, except this angle information. Rest things are very much same, right? So we have to uncompute. That means what? That means there is, I have already designed a circuit where the phase information is encoded, but there is an additional term 2 to the power n, right? That is coming in the numerator part, right? And the phase is encoded. So this is something similar to QFT, quantum Fourier transform, right? So what I'll do, so what I have done this. I have started, sorry. I have started with 0 state. I have done, suppose there are multiple states. Suppose I have done this Hadamard. I have taken this state ket psi. I have done multiple U operations, successive U operation, 2 to the power n minus 1, 2 to the power n minus 2, up to U 2 to the power 0, right? And I have done controlled operation, right? So I am here. Now this is very similar to what? QFT. Now if I place a inverse QFT circuit here, right? QFT dagger. If I apply a inverse quantum Fourier transform here, so this mathematical part that I have derived will be complemented by this QFT dagger. So this will be eliminated. Everything will be eliminated. What we will be left out? So we'll be having only 2 to the power n and this phi. This particular state will be getting. So this is the this particular, I mean the phase from the state. So I should not write in this Ket format, but 2 to the power n phi will be left out. Everything else will be out. So this is the only remaining part that will be having out of this circuit. So first part is similar to what we have done QFT. If you multiply this thing with the QFT dagger, so QFT times QFT dagger, they are unitary matrix, they will be cancel out. Only the additional part that is coming in the e to the power phase factor, and that will be getting as in the output, right? So the entire circuit, first part is similar to QFT, and the next part is QFT dagger, and at the end you can estimate the phase out of the circuit, right? So now let us do a quick summary. So in QFT, if you start with plus state, you will be getting 0 state, you will be getting plus state. If you start with 1, you will be getting minus state for the single qubit, right? And the Hadamard expression, we have learned that Hadamard gate in general, it can be represented e to the power 2 pi I xj gate 1 by 2, right? By square, so by 2 to the power 1. So I can cancel out these two things. So square root 2. So in this format, and another thing is that is important is that that I have just derived this this 2 to the power n times the phase factor, right? Also note that this e to the power 2 pi I times z, if z is some integer, right? Integer. So this is equals to in fact 1. Okay, so this is a periodic function, right? So sometimes we'll be getting the periodic information if this particular thing is integer, right? So, and this particular condition will be using in the source algorithm, will be showing there how it is used. Okay, so basically you will be using the phase estimation circuit, but so e to the power this 2 to the power so what is the expression just we got? 2 to the power n times phi, right? 2 to the power n times phi. And this phi is coming from the gate that you have used. So something like say 1, 0, 0 e to the power I phi. From there, this phi is coming. This might be unknown to you, right? Or this you may, if you know this, then there is no question of estimating, right? So now the thing is like if you express these things as e to the power 2 pi I z, so z is an integer and it's a periodic condition. So if it is 2 pi, every time it will be 1. So there is a relation, right? So for example, if it is e to the power 2 pi I, 5 by say 2 square, right? And Ket1. So this is same as e to the power 2 pi I, 1 plus 1 by 4, right? Um, that is very similar to e to the power 2 pi I, 1 by 4, right? So same thing, periodicity, because of the periodicity. So assume that we can prepare this state psi properly, and we can create the operator u, then we can estimate this phi. So this is the circuit for that quantum phase estimation circuit. And basically QP, what it gives, QP gives us an estimate of 2 to the power n phi. So whatever result you will get, if you divide by 2 to the power n, so if n is the number of qubit, whatever result from the probability you are getting, just divide with 2 to the power n, you will be getting the precise estimate of your eigenvalue, okay, of u. So this is for that. And there are two to three things that we need to notice. One is that 2 pi I theta, this part, or I phi, this part. So this part is basically this is important because sometimes whenever you will be designing circuits, you will see that some of the gates you are choosing in the quantum circuit, they may be in this form. So 0 e to the power I lambda form. So there is 2 pi is missing, right? So accordingly, you have to design the parameters and all. So when you need to multiply or you need to divide, that we need to keep in mind. Inverse QFT gives the initial state. Why only phase? Please explain. So the thing is, just to compare this two equations. So if you see these two equations, so this part, just this equation versus this equation. So see, just take a first qubit, the information in the first qubit. That's all. Ket0 is common, right? Exponential is common, right? So then what is coming here? So this Ket1 is common. Just compare this numerator part. So numerator, if you compare this part, so additionally what is coming? You have a 2 to the power n minus 1, right? 2 to the power n minus 1 by 2, right? And also you need to compare this. There is a 2 pi additional part here, right? So in the QFT picture, that is not there in the in the in the actually QP. So if you multiply this way, you will be getting that there is a this phi part is extra coming out of the IQFT figure, because that is not there in the QFT, that you can cancel out, right? First of all. Secondly, actually, I cannot do QFT dagger in the order QFT works. So what is happening? There is a bit mathematics. So let me tell you that part. So in mathematics, if there are two operators or three operators, say A, B, C, and if you take the dagger operations, right? So then basically this is C dagger, B dagger, A dagger, right? So the way we design the QFT circuit, in fact, IQFT will be reverse of that. Okay. So then basically you can compare easily that if you multiply the IQFT and so the first part of the QP and IQFT or QFT dagger circuit. So QFT dagger circuit is just not the inverse of the QFT, but it should also follow this mathematical principle, because when you design the QFT dagger, you will be using multiple quantum gates, multiple Haramat and phase gates, and the orientation should follow this mathematical principle, right? So then you will basically, if you compare the equation, so you can get back all these terms. So I'm not going all this individual component. I'm referring the book by Aijang Chuang. So that book and Nielsen. So please visit this book, and this entire derivation is there. If you are interested, please look at this, how this entire multiplication is done and how you are getting back this to the power n phi. So just I just told you the hints how to do this, because just comparing these two equation, but this is note that this is a QP versus QFT, right? QP versus QFT, but actually the comparison will be QFT dagger versus QP when you just match all the terms qubit versus qubit, right? Qubit to qubit, right? So also another important part is, for example, the quantum counting algorithm. Quantum counting algorithm. So quantum counting algorithm, same as the QP circuit. It is a QP circuit, quantum phase estimation algorithm, with Grover's rotation operator, rotation operator instead of U, instead of U. So that is called a counting algorithm, or Grover's search algorithm, or Grover's counting algorithm. What it does, same thing. You start with all Hadamard, right? 0, and then instead of U, you put a Grover operator here and do a controlled applications, uh, controlled controlled unitary operation. So again, if it is 2 to the power n minus 1, so it another Grover operator 2 to the power n minus 2 up to Grover operator 2 to the power 0, and you do in the second qubit control here, last qubit control, you'll be doing all the way you do the rotation operations, accordingly you'll be getting the information out of this. So this is very same as the QBE circuit. So two homework I am giving you here. One is there is no marks for this, but this is very helpful. One is the swap test circuit. I already probably covered it sometimes back. So the circuit is something like this. You start with the kits 0, and you apply a Hadamard here, and you apply a swap gate here. Instead of U, you apply a swap gate here, and you take a state, say X, and you take another quantum register Y. Okay, you put another Hadamard gate and do the measurement and see what is the output. It will give you quantum correlation, this particular probability output. You will be getting this inner product of these two vector. Okay, just check this one. Another is the Hadamard test. These two tests are very, very important. Suppose this is just 0 state. I apply a Hadamard here. Okay, those who could not draw, just let again draw this thing, and Hadamard here, do the measurement. Take okay, take a operator A as a control operator. Okay, and check that whether you are getting some state. If this is a X state, okay, what is the output? Okay. So let me just check this circuit. So this should give us X, A, X, this expectation calculation. So initially we have seen the combinatorial optimization problem, this kind of problem. So if this is your eigenstate, in fact, you'll be getting the eigenvalue here. So this is a Hadamard test circuit, and output will be square of this probability. So this is another important application of QP type circuit, right? This is a Hadamard test, and this is a swap test, and these are very, I mean, these are common across quantum chemistry, quantum machine learning literature, and you can make use of these things. So now, okay. So after this QP, as I promised, so I'll go back directly to the question asked bit earlier, 30 minutes ago, how the periodicity is coming in source algorithm, that part. So take a 1 minute break. So it's not actual break, 1 to 2 minutes. So I'll go back to that particular topic. Okay. Any question? Um, Somebody asked, give an example of source algorithm. Okay. First of all, source algorithm is a fault tolerant algorithm. You cannot implement right now. You need to wait for noise-free qubit or more huge number of qubits. Secondly, applications of source algorithm is in the RSA decryption thing. So it's in the crypto breaking cryptographic key and all. Okay, I'll come to that point. Somebody asked, why is the ordering of qubits differs in books and IBM Qiskit? Can you avoid swap operation? You cannot avoid swap operation. So if you want to implement, so in books, things are written in idealistic way. When you implement, you will realize because everything when you represent in the binary string format, the information in QFT just it does the reverse operation. So for that you need to do the swap operations at the output in order to get the result in order. Else for the short circuit, like small size circuit or short size circuit, what you can do, you can manually design quantum Fourier transform accordingly the equations that is written in the books. But again, automatic that equations requires the swap performance. So manual doing may not need the swap operations at the output. So yesterday I gave some code example. You could see from there. Explain the practical applications. Okay. Okay. So maybe I can share this PPT that might be helpful. So the question, the applications of source algorithm is the same as like asking what is the application of a plus b whole square, something like that. Okay. So this is a one primary foundational algorithm for period finding. In fact, for period finding, why source algorithm? You can directly use the quantum Fourier transform. That is the building block for source algorithm. Source used this QFT conceptually to find the prime factorization specifically. Okay, so okay, I am not going to RSA part because this is beyond syllabus, so encryption part. But just note that so this is just an as an application as you just asked. Okay, so okay, there are many questions. I have one question on constructing the oracle. I tried. Okay, oracle construction is a challenge. So because all these algorithms are fault tolerant, so implementation is not that easy. Like how you access the oracle and all. There are some applications, the implementations done by not IBMers, so it's externally done or something like that. There are certain Qiskit links as well. But yeah, I mean, we need to wait a bit for the fault tolerant era to see the applications, TL applications of these kind of algorithms, QFT, QP, Grovers. Especially in Grovers, the Oracle preparation is a very tricky step. Yeah. Um, hmm, can you please share the PPT material in Canvas? Yeah, I shared the PPT to Professor Pillai sir. He'll be sharing. Okay, so in RSA, basically, this RSA is one of the encryption algorithm widely used today, where basically large number of quantum key, right, or security key is prepared. Where the large number, okay, let me, is there any pen here? Uh, I don't know. Let me check this. Highlight pen. Uh, So that is so basically sorry. So basically n is a large key size and which is a product of two or multiple prime numbers, right? And computes. So these prime numbers, finding the prime numbers is basically classically hard, as I told you yesterday. It's exponentially hard and classically based on the hardness of the computation of the prime factors. people design this RSA encryption and decryption techniques, right? So I'm not going detail to that, but um, so if you do classically, it's exponential, this particular order. So e to the power some constant, log n to the power half, log n to the power half. So using the best classical one of the factoring algorithm, that is called the quadratic sieve algorithm, or the field sieve algorithm, that is there with log n to the power one third and log n to the power two third, right? So even classically, it's almost very difficult if your number of key, that is n, is very high, right? So, if you apply the quantum Fourier transform based or the quantum phase estimation based source algorithm, okay, I'll write the steps. Don't worry. Just people asked for the application, so I come to the application part first. So you leverage the superposition and entanglement to encode your information and to basically get back the phase component or the finding the periodicity. And why the periodicity is important here, I'll come back again. So it gives you a polynomial kind of complexity order of n to the power slightly less than order of n to the power 3. And so basically order finding problem is basically this modulo, basically any number a to the power r, where r is the order of a is some coefficients and r is the order of the number, you can represent as 1 modulo n. This is a CS format of writing any number. And what is that? I'll come back. I'll explain by, because this PPT explanation is very difficult. So I'll again talk with pen and paper, just covering the PPT, just an example. So now this is a basically periodic representation of a number. Okay. So this is what is that and all, I'll come. So then basically, if you apply the quantum Fourier transform to find the periodicity, how the particular reminder is repeated or the coefficient is repeated, you can compute that periodicity. Once you do that, then basically you from the measurement, quantum measurement, you calculate various other parameters, especially the order R, and then basically you do the modular exponentiation. So that is taking roughly the polynomial complexity. So basically the use case is that if you have a large number, so you can use source algorithm to factor that particular large number to the prime factors. So that's the direct application of source algorithm. Okay. uh, of course, there might be other applications, so I'm not covering that today. So now let us come back this modular representation technique, so that okay. So now let's go back to source algorithm part again. So once you know all the component of source algorithm, then things are done. There is nothing new. And two most important component we already have done, QFT and QP. Okay. Now, those who are not from the computer science background, so this may be helpful for them. Though those who already know this modular exponential representation, this is just a basic concept, so you don't need this particular next 15 minutes lecture. So this 5 divided by 3, for example, like arithmetic computation, simple division. So what is the answer? So 5 divided by 3 is 1 and 2. So 1 is basically the quotient is 1, and the remainder equals to 2, right? So you all know these things, right? From our school, primary school level, we know these things, this arithmetic division operations. So the computational way of writing this as this way: 5 equivalent to or equals to, you can say, 2 modulo 3. 2 modulo 3. That means if you divide 5 by 3, you get the remainder 2. As simple as it is. Okay. So now we'll be following this particular representation. This is easy to represent on our digital computer. Okay. Suppose X is a number, and the set of numbers basically is a series of numbers. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are series of numbers. Okay, just be patient for 5 minutes and you will understand what is periodicity, why they come here, why I use quantum Fourier transform. All the answer will be clear here. Now, now suppose I divide this with the number 3. That means modulo 3. Okay. If I do modulo 3 for this series of number x, what I'll get? So x equivalent to, I can write. So if you divide this number with 3, so basically you will be getting zero answer. I mean, so for example, if it is 1, you will be getting the remainder 1. If it is 2, remainder 2. If it is 3, there will be no remainder. If it is 4, again you will be getting one remainder, because 4 divided by 3 will be so basically 3 and 1, right? So 1, again it is 2, again it is 0, again it is 1, 2, 0, like that. So all the multiples of 3, 3, 6, 9, they have zero remainder. All this number, if you see, so say for example, here if you see and here if you see, so this number is repeated, right? 1, 1, 2, 0. The remainder is repeated, 1, 2, 0, 1, 2, 0, 1, 2, 0, and so on, right? So if I see from here to here, there is a repetition of things pattern, and this is the period of this series with modulo 3, periodicity. With period equals to 3 here, right? So now, so let us write certain things. X equals to 0 modulo 3 means x is a multiple, x is a multiple of 3. You see all the numbers 3, 6, 9. So if the remainder is 0 with modulo 3, that means x is a multiple of 3, right? So you can write all those x as 3k, right? So I'll write it later. Okay. So then if I say x equivalent to, or x equals to 1 modulo 3, that means x is a multiple of 3 plus 1. Okay. So how I can generalize these things? How I can generalize these things? I can say x equals to y modulo 3, y modulo 3. That means x equals to 3k plus y for k equals to integer. Okay. So if k is an integer, you can see, you can represent any number x. If x is y modulo 3, that means x equals to 3k plus y. If it is 3k plus 1, if it is 3k plus 0, this is 3k plus y. Okay. So this is a general representation of the numbers in the series, right? So now if it is not modulo 3, it is some modulo n. So you can see, you can check the periodicity, right? In this series, right? From here, just I have drawn these things, how this periodic repeated for the 3 modulo. Now if it is x, if you can represent x equals to y modulo n, right? Means you have a series of number y from 0 to n minus 1, right? So such that it is basically, you can write y x equals to basically n k plus y in this particular way, right? So for the 3 particular case, if modulo equals to 3, and we have seen that the series of numbers y can be 0, 1, or 2, right? Remainder can be 0, 1, or 2. So this is the way how we write the things in the modular representation of numbers, right? So now basically let's do the source algorithmic steps. It will take 2 to 3 minutes. So if you have a large cryptographic key n, and n equals to p into q, right? So where I don't know the p and q, and finding the p and q are exponentially hard, right? So what it does is that first step, okay, pick a number A, Just choose particular A, choose some A, choose some A, which is, that is co-prime with N. Co-prime with N means there is no common divisor. Okay. Then find the order. Find the order. It is related to the periodicity. Okay. Find the order R of the function. You define a function a to the power R. Okay. Modulo N. This is the representation of a function in the exponential representation of your function in the periodic form, right? So find smallest R such that a to the power R is 1 modulo N. We have to find the smallest R such that the remainder is 1 with the modulo N, right? Third step is, if R is even, so this is a good approximate, then X will be a to the power R by 2. You can basically design in this way, modulo N and X plus 1 will be so if the condition is it is even, or then this case, or the if it is odd, then X plus 1 not equals to 0 modulo N, then that is a better solution. Then we can say that P and Q, the factors contained in, or at least contain in the GCD of X plus 1 and N in the even case, or in the odd case GCD X minus 1 N. Okay. If you don't get the solution, then else choose some other. Okay. So that is source algorithm. Basically, these are the only four steps of source algorithm. But the main fundamental is finding the order R, which is the periodicity. You can see, right? And that we have checked that if you have an arbitrary encoded state ket psi where the periodicity lies, and that periodicity you can find out through the quantum phase estimation or the QP, in fact. That particular phase where the periodicity lies, right? How it is repeated and all. So that is basically the source factoring algorithm. So the direct application is basically finding the prime numbers, prime factors of a big number. And this is like computationally, or from computer science angle, this is one of the most challenging problem to earth, right? Now we have also learned many things. One is the quantum Fourier transform we have learned. We have learned this quantum phase estimation, their extension to Grover's, their extension to this Hadamard test, their extension to Swift test, and all these subroutines are hugely used in quantum chemistry, commutative optimization, problem solving, and all. So hence, I'm just concluding these portions here. And if you have any questions, so please feel free to ask me in the chat. Okay, so there is one question. Can you explain the first 2 points? So basically, like if you have a large number P and Q, right? Large number N, and there is a factor P and Q, but you don't know what are P and Q, right? How you have to find P and Q. Okay, so you choose a particular coefficient or a co-prime number A, which is co-prime with N, and then you represent that number in the modular form. That I explain how to represent a number in the modular form. But I have written in the a to the power R modulo N such that you can find the periodicity when the number is repeated. Okay. And the objective is to find the smallest periodicity, like the R, right? Then you can find the region, and you can make the, like, you can shorten the region using the GCD, using step 3 and onwards, right? Yeah. Okay, IBM URLs, I'll check and forward to Professor Pillai sir, and I hope he will be sharing it with you all. So yeah. So source algorithm is right now difficult to implement because of the huge circuit depth. That is the availability number of qubit, good quality qubit, good quality number of gates, good number of gates. So we need to wait for a couple of years to implement this kind of algorithms. First of all, if n is small, there is what quantum advantage is there? If n is large, then it is computationally difficult, exponentially hard, right? And the source algorithm is a polynomial speed up algorithm that we have initially seen, right? So it's roughly slightly less than n to the power 3. Okay, it's basically n square log n, something that kind of thing. So hence, if n is very large, then you can compare with the classical complexity that it's giving good result. Thanks. Yeah, so the detailed is how you do the prime factor. So I need to again explain the RSA and all these things. So this is the beyond syllabus. So maybe sometimes later we can come back again. So you need to iteratively run these things. And every time you need to estimate the phase and estimate the periodicity out of this algorithm and find the smallest one. How much is used to? Okay, there is I forgot the name. I'll share somebody explains which a quantum theorist, information theorist, and showed that at least next 10-15 years our encryption is safe. It is not that easy to implement Shor's algorithm effectively. But again, in the next course, there is QT-06. There, I hope somebody will take the portions that is called the PQC, post-quantum cryptography, or the quantum safe cryptography. You'll see there are other encryption key people are trying to implement or design, which avoids the periodicity condition. Okay, so those cases, this source algorithm will not impact as such. How source algorithm or how it helps in QFT? I think QFT is a building block of source algorithm. How source algorithm can help QFT? I hope you got the answer. So it's the question is something like how I can help my heart, right? Or how I can help my liver, right? So my heart is helping me, right? So it's a building block. QFT is a building block of your source algorithm. So QFT is eventually computing the periodicity part of the source algorithm. So typically in the QFT, I showed how to compute the frequency, right, or the periodicity for a given signal. So instead of the signal, you take a series of numbers and the numbers represented in the modular form, right? So it's not a direct design. So you need to convert things to binary settings and all. Yeah, so those who wish to communicate through email, I am giving you two emails. So one is for the official purpose, like any engagement or anything, this one. And if you have general query, so because of I have email box as well as the drive. So so this one, second email is for this is for the general query or anything. Um, and also I can share my, just 1 minute. My web page as well for any other details, publication. Sometimes I put tutorials, anything. So yeah, you can contact me. Thanks. So Sivan sir, anything? Shall I wait or just close the session or like?